My name is Evert Boymans. I work at TNO in the biomass group. Formerly, the group was also known under the name ECN. My talk will be today on the gasification of energy crops and the required gas cleaning, with a special focus on the sulfur removal that is required to produce a syngas that is ready for Fischer-Tropsch synthesis, or the production of liquid fuels. So the experimental work that I will present is part of the BECOOL project. This is a project that focuses on the production of liquid fuels from lignocellulosic biomass. It's quite a broad project. It consists of the production of biomass, which can be seen as the first pillar. Then it also includes work on logistics, so the harvesting itself of the different types of biomass. And finally, the third pillar is the processing, which is the thermochemical conversion, which basically means gasification, followed by gas cleaning, and finally Fischer-Tropsch synthesis to produce kerosene. So for the routes that were selected in the thermochemical conversion, as shown also in the previous presentations, there is, in terms of the processing that is required, is a multitude of possibilities. So within the project, we selected a few routes that we highlight and investigate. So this is chosen together with the project partners such as VTT. And the two main routes are first of all pyrolysis, followed by train flow gasification. Pyrolysis is kind of seen as a biomass pre-treatment that can take place decentralized close to the biomass source. And the second route, route B, is the direct solid biomass gasification at low temperature, which requires gas cleaning, which can either be direct cracking of the gas into syngas, or another option is B2. Option B2 is the scrubbing, so low temperature gas cleaning, followed by gas upgrading and Fischer-Tropsch synthesis. So looking at the second, so the process shown here includes the indirect Milena gasifier. It can directly process solid biomass into a producer gas. So the gas, because it's low temperature gasification, contains also tar and other impurities, lots of hydrocarbons and BTX, ethylene, etc. This needs to be followed with tar removal, which is called, in this case, the technology is called Olga, followed by condensation of the water, because the tar removal takes place above the water dew point. So this technology is already patented and is licensed actually by a company called Sinova. Then further on to process the gas, the sulfur removal is a very important step. And here the choice has been hydrodesulfurization, the HDS, which is a catalytic conversion, converting the organic sulfur into H2S and COS, which is then captured by a zinc oxide sorbent or another sorbent. The sulfur removal has already been established and used prior in wood gasification lineup. Then it works, so the sulfur can be removed up to ppb levels. However, the big question is, with different types of biomass which are not wood, does it also work? That is actually the main question I will look in the following slides. Overall, such a process that we're looking at here, as for modeling, we know that the overall efficiency is about 45%, carbon efficient 34%. Seems quite low, but of course there is quite energy densification, as the starting wood is about 18 megajoule per kilogram, and the liquid product, the Fischer-Tropsch liquid, has an energy density of about 43. So the types of the biomass that was used in the experiments are shown here. So these were kindly provided by the University of Bologna. These are eucalyptus, biomass sorghum, and giant reed. As the experiments took place at lab scale, the lab scale steam gasifier can handle about 5 kilograms per hour of material. And for woody biomass, it can just be chipped into millimeter-sized particles and then be gasified. For the other two biomasses, so the sorghum and the giant reed, it's very fibrous material, very harsh, and just chipping it and grinding is not enough, because it leaves a lot of fibers that cannot easily be fed into the gasifier. So that they needed to be pelletized and ground. It's quite an intensive process to get that done. And then they could also be processed in the gasification. If you look at the approximate and ultimate analysis of these feedstocks, as expected, as can be expected, compared to woody biomass such as eucalyptus, the ash content is much higher, and also the sulfur content is much higher than is present in wood. And of course, this high sulfur content will then from the biomass end up also in product gas, so it requires additional processing. Or that is the question: does it need additional processing? And what are the consequences? So this was for the experiment that I will show today. There was a one-day experiment with sorghum. As shown earlier, it's a gasification followed by, in the Milena gasifier we call it, followed by tar removal, water condensation, pressurization, and then the catalytic HTS, which converts the organic sulfur such as mercaptanes and thiophenes into H2S and COS, which can then be captured by the zinc oxide bed. For the HTS reactor, what we know, of course, as I mentioned earlier, it converts the organic sulfur into H2S and COS, so that it can be captured by the zinc oxide. Typical temperature range of this reaction is about 300 to 500. We are at 450, so close to the maximum temperature. And in general, higher pressure and higher temperature are favorable for the conversion. Not only organic sulfur, but also ethylene and unsaturated hydrocarbons are hydrogenated in this reactor. And no additional hydrogen is typically required because there's hydrogen in the gas, so you don't need to add an extra gas. So just quickly, the gasification, there's no big differences between the fuels. Typically, the gasification takes place at 800. Carbon conversions are in the range of 70–80%. Interesting is that for the non-woody biomass, almost all the sulfur that is present in the biomass also ends up in the gas. So looking at the product gas, the sorghum, and the performance of the HTS reactor, shown here is the gas composition prior and downstream of the reactor. And as can be seen, the concentration of H2S is really high, it's almost 1000 ppm. And especially the concentration of methyl mercaptan is very high, and the thiophene is quite high, not very high. The conversion in the HTS reactor towards H2S was initially very good, but then during the day when sulfur breakthrough occurred, so HTS catalyst is a cobalt molybdenum oxide catalyst, I forgot to mention that. It not only converts sulfur, but initially organic sulfur, it initially also absorbs some sulfur. And what we noticed is that during the day, when the breakthrough took place, the activity of the catalyst decreased. So looking a little bit closer to the results, we analyzed the gas online with the micro GC, and on the left-hand side you see the H2S concentration upstream of the HTS reactor and downstream. And what you expect is actually downstream the concentration is higher, but because initially the bed also absorbs sulfur, you can see that the sulfur is being absorbed. But then during the day, actually the breakthrough of H2S occurs, and it's exactly at the time when also the activity decreased. So we expect that this has to do with the very high sulfur concentration in the gas, which starts to increase during the day, which causes this decrease in activity. So for the conclusion, the gasification of all three biomass were successful. Typical carbon conversions are in the range of 70–80% at 800 degrees. Sorghum and the giant reed did require a pelletation prior to feeding it to the gasifier, but that's especially a small scale issue. As could be expected, just switching the type of feedstock does not mean that you can use the same technology for the removal, in this case, of sulfur. There are definitely consequences that sulfur concentration is that high. Also, the hydrogen concentration, which is causing the deactivity of the catalyst, is not as high with sorghum. So the combination of both makes it that the removal of the organic sulfur is not below or up to ppb level as you would desire. So there are straightforward solution that just needs. We do think eventually the HTS reactor can work also with different types of feedstock, but either the pressure has to be increased, or the overall, or just the hydrogen pressure, or the bulk sulfur removal has to be performed upstream the reactor, so that the HTS does perform as we desire. So that means up to ppb levels of organic sulfur. Finally, I just want to thank my colleagues, especially Herman, Dennis, Marco, and Arnold, who actually did the experimental work in the lab. So I want to thank them very much. Finally, I want to thank you for your attention and all the project partners.